Hello everyone, this is the first video of our last lecture and I want to devote it to reweighting as one of the possible strategies adopted in order to be able to say something about what happens at small values of quark or baryon chemical potential, starting from simulations that are run, for instance, at mu equals 0. Yeah, so one video to go. It will be about Taylor expansion, but let's focus on reweighting first. So the leitmotif is circumventing the sign problem, and particularly in regions where we know or we have reasons to believe it is not severe, and then it is doable to circumvent it with methods that are based on standard Monte Carlo. And what we know is that colder and denser QCD states stay inaccessible because the severity of the sign problem in that regime is such that one cannot think of applying this kind of methods such as reweighting and Taylor expansion. However, hotter and diluter QCD states, so basically this area of the sketch of the phase diagram, are accessible either with reweighting. QCD and phase quenched QCD are alike in this regime, just to mention this, and or with Taylor expansion, which exploits the relative smallness of mu with respect to t, and then it works good at small q and large values of the temperature. Okay, then the question is what kind of interesting physics can we learn when we are in the hot and dilute regime of QCD? Well, starting from the phase diagram, just to talk about phase diagrams, there is this crossover at physical quark masses. The sketch is thought for a setup with 2 + 1 physical quarks. And it happens that this separates the hadronic from the QGP phase, and at small mu q, it bends towards lower temperature, possibly terminating in a second order critical endpoint. Bear in mind, we are talking crossover, so different observables might give different values for the critical temperature, the temperature which is at the boundary between the hadronic phase and the quark-gluon plasma phase. So taken all together, the observations that we can make based on different observables, we have actually a region, a band, which we can identify as crossover rather than a boundary, a one-dimensional manifold in the plane. Yeah, and we can look at that. I will use TC, but bear in mind this is a crossover also in the thermodynamic limit, so TPC would be a better terminology, a better nomenclature, a better notation for the temperature at which you go from hadronic to quark-gluon plasma phase, close to the temperature axis in the sketch. Okay, so here I'm showing something that we have seen already, and that is sort of what reweighting relies on, even though we will generalize it in the next slide. You have a complex phase and you absorb it in O. So you split the determinant into something which is real and positive and a phase, a complex phase. And then you write the expectation value of a generic observable in a way that the modulus is used for sampling in the Monte Carlo Markov chain simulation, while the phase is, together with the observable, our more complicated observable. And then also the denominator, instead of having just the partition function, you have the phase quenched, so-called expectation value of the phase itself. Okay, what PQ standing for phase quenched means, again, is that only the modulus enters the weight. Okay. We have already discussed that there is an important caveat to this that might look like an easy way out to the sign problem, and this is in the overlap problem, because what we have at the denominator, for example, is just the ratio of the full over the phase quenched partition function, which is something that goes exponentially with the volume and the difference in the free energy density. And if it goes exponentially in the volume and we have to take the thermodynamic limit, then it's over. So sampling with the wrong weighting factor, we said already, can be exponentially inefficient, and it only works decently as long as the difference between these two partition functions is negligibly small. Okay, more in general, let us now consider the determinant together with the exponentiated gauge action. And let's call this omega as a function of mu q. And this is a complex quantity because we have a quark chemical potential which is different from 0. Then we again evaluate the expectation value of a generic observable. This is our complex weight, and what we do is we introduce R, which is a real and positive function even at non-zero mu q, in a way that we have the ratio of W over R, which is absorbed, which is considered as an observable, and at the numerator and at the denominator. And what we are doing is we are taking ensemble averages using this R as a function of mu q, which is by construction real and positive, as a Boltzmann probability distribution function. Okay, again, we have exponentially severe overlap problem. This is just the same expression as before, written in more general terms. And we look also in this case for a measure of the severity of the sign problem to the average reweighting factor, pretty much as we did before by looking at the average phase. And what is the average reweighting factor? It's written on the slides. Again, ratio of two partition functions, this time z omega and z r. And this is again exponential in the volume times the difference of the energy densities, which is greater or equal than 0. Again, same considerations as before. It only works decently when the differences between these two partition functions are small. But now this is general, so you are not just using the absolute value for weighting and the phase of the complex determinant for the observable, but you are rewriting this in a more general way. And one must consider that different choices for this omega over R ratio can correspond to a more or less severe overlap problem. So in principle, one might think of a good way, a good reweighting, where the reweighting factor and the average reweighting factor, that's a measure of the severity of the sign problem, is telling us that the sign problem is not so severe. So now that we have understood how it works, let's think about the pros and cons of tackling the issue of establishing what happens in the phase diagram at small values of the baryon chemical potential with reweighting. A good point of reweighting, and for example, an advantage of reweighting with respect to Taylor expansion, which we will discuss next, is that there isn't any systematic error besides the overlap problem. As opposed to Taylor expansion, as I said, because in that case, when you Taylor expand, you in principle have an infinite series and you truncate it somewhere, and that truncation leads to systematic errors that you need to take into account, and this you don't have in the case of reweighting. The other good point of reweighting is that, in principle, it gives correct results in the limit of infinite statistics. And therefore, it can be used as a brute force approach to the sign problem. But due to the fact that it can be exponentially inefficient in the volume, one needs to be aware of that. Plus, it certainly does not solve the sign problem. It is just a way to circumvent it. Okay, and with that in mind, let us look at what are the explored choices for the reweighting factor in the literature, at least a couple of them. In particular, I wanted to mention to you the Glasgow reweighting, which is a reweighting that happens at fixed temperature. So in that case, the ratio omega over R is just the ratio of the determinant of the Dirac operator for mu q different from 0 and for mu q equal to 0. However, the issue with this kind of reweighting is that Z omega and ZR becomes very soon very different if Z omega corresponds to the high mu Q phase. So it has been explored, but it didn't give very satisfactory results. On the other hand, there is another option, which is the so-called multiparameter reweighting. Why multiparameter? Because also beta and not just mu Q is varied. And in particular, this reweighting is done along the crossover line for one specific observable. So it is done along TC as a function of mu Q. That means that we have in the reweighting factor not just the ratio of the two determinants, but also the exponential of the delta gauge action. What is the advantage of proceeding like that? The advantage is that both partition functions, the omega and the R partition functions, are aware of the hadronic and of the QGP phase due to the fact that this reweighting is done along this crossover region. And reweighting transition configurations to transition configurations brings an advantage because it just has a less severe overlap problem. So in multiparameter reweighting, what is done in practice is that one has ensembles of QCD configurations which are produced at mu Q equals 0 and at the temperature at the edge between the hadronic and the quark-gluon plasma phase. And then from there, one starts reweighting at mu Q different from 0. And at the same time, one lowers the temperature because we know that this crossover is bending down when one goes in the direction of the quark chemical potential. And you get good overlap out of the fact that, as I mentioned, transition configurations are reweighted to transition configurations. This was really then used in order with the ambitious goal of identifying the critical endpoint. And in particular, the critical endpoint was located in a setup with which was like a rather coarse lattice with physical strange quark mass, but only semi-realistic up and down degenerate quark mass. It was back in 2002, and these were rather expensive simulations back in the time. What was the strategy, though, for locating the CP? This is the important piece of information that I need to provide you with. So the type of the transition as a function of the chemical potential is obtained in this kind of investigations from the volume dependence of the complex Fisher zeros of the partition function, Z, as a function of the unphysical complex gauge coupling beta. So the coupling is complexified. And at that point, you can look at the zeros of the partition function, which is now the function of a complex gauge coupling, and you can look at how they move or evolve towards the thermodynamic limit. And the critical endpoint, the value for the chemical potential at the critical endpoint, but also for the temperature at the critical endpoint, is the value at which the crossover disappears and the thermodynamic limit scaling predicts a first order phase transition. And this corresponds in the Fisher zero language, which is just an alternative way of locating a phase transition, to the accumulation of the zeros near the real axis. Okay, so you have Z, it has zeros, they change when the volume is changed. And if, while the volume is tend to infinity, these zeros of the partition function accumulate near the real axis, so on the real axis, then it means there is a true phase transition. Otherwise, you still have a crossover. And this was exactly the idea that was used in this investigation to identify the critical endpoint. What are the tricky points in this prediction? First, that this was done with 2+1 flavors of staggered fermions, for which you need routing. And when you take the root and you have complexified the parameter space of your theory, then you run into the ambiguity of taking the routing of which branch to consider. And the authors of this paper basically considered the root that was connected to what they were obtaining as a root at mu q equals 0, but that is just a possibility. And also the inexact R algorithm was used in this case in the Monte Carlo simulation as opposed to the exact RHMC simulation. Now, if we were back in 2002, this would be the end of the talk, of the slides, and of this video today. But recently, this whole investigation was revisited. In particular, in the new investigation, both unimproved, like in the 2002 paper, but also stout improved staggered quarks were used. And the algorithm for the ensemble generation was the R algorithm in the 2002 paper, and it was replaced in 2020 with the exact RHMC algorithm for the 2+1 fermion species setup. Not only, but a geometric matching method was proposed in order to solve the analyticity issues and this ambiguity when taking the root of the fermion determinant with staggered. Well, I must say that there are good and bad news that came out of this investigation. So first of all, previous results were confirmed for the case of unimproved staggered fermions, and this confirms the method, and in particular, it's telling us that this geometric matching method sort of corresponds to the way or to the procedure that had been identified in 2002 in order to remove the ambiguity. The bad news is that the overlap problem worsens under improvement at fixed thermodynamic state. And there is an interesting view of this fact because you might remember in the Columbia plot, we have the first order region in the chiral limit, and we looked at it and we said that this has a very strong cutoff dependence, and in particular when we go towards the continuum limit, that area shrinks, that first order region shrinks. And so what happens from the point of view of the physical point, because in this paper then physical masses were simulated, is that the critical value of the quark masses were, by critical I mean that is the value where a true phase transition takes place at mu equals 0, is pushed away from the critical point under improvement. So what happens really is that the leading Fisher zero, which is defined to be the closest one to the real axis, is moving farther away from the mu q equal 0 thermodynamic state. And this, as a consequence, leads to poorer sampling at mu q equals 0 of the relevant configurations that carry the information on the existence of the critical endpoint at mu q different from 0. So what we are observing is, in the end, is a manifestation of the overlap problem becoming more severe due to that ratio of partition function that is always the crucial point in reweighting to establish the severity of the overlap problem. So I would, my final take on this kind of investigation is that they're very interesting, but there is this one big main obstruction, which is that at the same time you need to take the thermodynamic limit because you really want to see these zeros of the partition function, these Fisher zeros, accumulating near the real axis as the volume is sent to infinity. And only if the imaginary part of these Fisher zeros in the thermodynamic limit becomes 0, you can say that you should expect a true phase transition. But the thermodynamic limit is precisely what worsens the overlap problem in an exponential way in exactly the same limit. So this is a very tough business, but yeah, I hope you got an overview about reweighting as a possibility to brute force your way out of the sign problem. It has pros and cons, and it might be very tricky to find out the right setup in which to do reweighting, such that the configurations where you can sample carry or know something about the configuration at your target point. But yeah, that's how it works, and we can discuss this further in the class as usual.